Welcome to the Wonder Lab, the place where curiosity meets the very fabric of reality. Today we embark on a journey that stretches from the invisible heart of atoms to the extraordinary phenomena of superfluids, where the rules of classical physics no longer apply, and the universe begins to feel more like a dream than a clockwork machine. Imagine for a moment a world so small that nothing you see, touch, or even imagine could exist there in the way we think. A world where particles behave like both waves and matter, where certainty is replaced by probability, and where the tiniest interactions can ripple across the cosmos to shape everything from the air we breathe to the glowing stars overhead. This is the realm of quantum chemistry, a world so intricate yet so fundamental that it quietly orchestrates the reality around us every single day. Let us start with the atom, the building block of everything. But don't picture it as a tiny solar system. No, atoms are not solid spheres. They are dynamic, vibrating entities made mostly of empty space, surrounded by clouds of electrons whose paths we can never pinpoint exactly. These electrons are more like dancers on an endless stage, weaving patterns and probabilities in constant motion. The way they arrange themselves, their orbitals, decides how atoms bond to form molecules. These bonds, invisible to our eyes, are the scaffolding of matter itself. Without them, there would be no water, no air, no life, and no story for us to tell. And yet, atoms do not dance alone. They are influenced by forces so subtle that they are nearly imperceptible, yet so powerful that they govern the properties of matter. Quantum mechanics teaches us that energy comes in discrete packets, quanta, and that particles can exist in multiple states at once, a concept so strange that it defies intuition. Imagine being able to occupy two rooms at the same time, or to be in two cities simultaneously. In the quantum world, such paradoxes are routine. Now consider entropy, the silent sculptor of the universe. Often misunderstood as mere disorder, entropy is actually a measure of the countless ways a system can arrange itself. It drives chemical reactions, dictates the flow of heat, and underlies the arrow of time itself. Through this lens, every cup of coffee cooling on your table is a demonstration of universal principles stretching from the tiniest particle to the grandest galaxy. Energy disperses, probabilities shift, and the cosmos unfolds with exquisite precision, even in apparent chaos. In this journey, we will also encounter phenomena so strange they almost seem magical. Superfluids, for example, flow without friction, creeping up walls and defying gravity. Bose-Einstein condensates, states of matter formed at near absolute zero, act as a single, unified quantum entity, blurring the line between individual and collective behavior. These are not mere curiosities. They are the windows into the hidden rules of nature, showing us what is possible when we push matter to its most extreme limits. As we move deeper, we will explore the interplay between chemical bonds and quantum uncertainty, how light interacts with matter in ways that can both reveal and conceal the secrets of molecules, and how scientists today manipulate these principles to design new materials, medicines, and technologies that were once only imaginable in science fiction. Every reaction, every photon, every electron carries a story, and together these stories form the narrative of the universe itself. Prepare to question everything you thought you knew about reality. Prepare to witness a world where the familiar becomes strange, the invisible becomes visible, and where the smallest components of existence wield the greatest power. This is more than chemistry. This is the architecture of reality, the poetry of particles, and the secret language of the cosmos. So, take a deep breath. Let your imagination stretch beyond the visible, beyond the tangible into a universe where curiosity is the only guide and wonder is the only destination. Welcome to the Wonder Lab, where the quantum world is about to reveal its secrets. As we step into the first chapter of this journey, we must begin by confronting a question both simple and profound. What is matter? At first glance, the answer seems obvious. Matter is the stuff around us, the objects we see and touch. But when we peel back the layers, when we look beyond the surface of the everyday, we find a universe far stranger than any fiction. Every object you touch, every breath you take, every drop of water that glimmers in the sunlight is built from atoms. But these atoms are not solid, unchanging blocks. They are dynamic systems, buzzing with energy, interacting through invisible forces, dancing in patterns that are at once orderly and chaotic. Imagine a bustling city at night, where each light represents a possibility, each movement a probability. This is the atomic world, alive, restless, and full of secrets. Consider the simplest atom, hydrogen. One proton, one electron, yet even this simplicity hides astonishing complexity. The electron does not orbit the proton in neat circles as once imagined. Instead, it exists in a cloud of probability, a haze of potential paths, each possibility influencing the other in ways that can only be described mathematically. And yet, this tiny particle shapes the fate of galaxies and the chemistry of life itself. Hydrogen bonds with oxygen to form water, the universal solvent that flows through rivers, nourishes life and carves mountains. As atoms combine, they form molecules, structures that are more than the sum of their parts. Carbon, with its unique ability to form four bonds, is the cornerstone of life. Its flexibility gives rise to sugars, proteins, DNA, and countless other molecules that form the blueprint of living organisms. Consider a single strand of DNA, a structure that contains the instructions for life. Its double helix twists and folds in precise ways, guided by chemical forces that seem almost miraculous. Each bond, each interaction, is a tiny act of molecular choreography, shaping the forms and functions of every living thing. But chemistry is not merely a story of structure. It is a story of energy, of electrons jumping between levels, of bonds forming and breaking, of light interacting with matter to trigger reactions that power stars and fuel life. The photons of the sun strike chlorophyll in plants, initiating a cascade of electron movements that capture energy and store it as chemical potential. This is photosynthesis, the invisible engine that sustains nearly all life on Earth. Without it, the planet would be a barren wasteland, cold and silent. Even in seemingly mundane processes, the subtlety of chemistry is profound. When you dissolve sugar in tea, the molecules disperse, moving randomly yet collectively, influenced by forces that are too small to see but too powerful to ignore. Each collision between molecules is a negotiation, a dance of attraction and repulsion, governed by quantum mechanics. Heat, the motion of molecules, shifts the probabilities, nudging reactions forward, guiding matter toward new configurations. And yet, the chemical world is not static. It evolves, adapts, and transforms over time. Consider the formation of crystals, where atoms arrange themselves in perfect lattices, repeating patterns that stretch for micrometers and beyond. Each crystal is a testament to the power of order emerging from chaos, or the formation of complex molecules in interstellar space, where atoms collide in cold, dark clouds to form compounds that may one day seed new worlds. Chemistry is the quiet architect of the universe, invisible yet omnipresent, shaping everything from the tiniest snowflake to the largest star. In this first part of our journey, we will not only explore the structures of atoms and molecules, but also the forces that bind them, the principles that govern their interactions, and the astonishing ways in which chemistry underlies every aspect of reality. From the subtle tug of van der Waals forces to the immense power of chemical bonds, we will witness a universe that is both elegant and intricate. A universe in which every reaction tells a story, every molecule carries a history, and every interaction whispers the secrets of existence itself. So, let us continue, moving deeper into this microscopic cosmos. Let us marvel at the hidden machinery of reality, the invisible architects that build our world, and the astonishing principles that make life, matter, and the universe possible. This is part one of our journey, the gateway into the wondrous and intricate world of chemistry, where curiosity becomes understanding, and understanding becomes awe. As we step further into the hidden depths of reality, we must confront a question that lies at the very heart of existence. What holds the universe together? Atoms and molecules, as we have seen, are not isolated. They interact, bind, repel, and dance under the influence of forces so fundamental that they shape every particle, every star, and every life form in the cosmos. Let us begin with the forces that act at the atomic scale, the four fundamental forces of nature. First, the gravitational force, weak at the scale of atoms, but unyielding across cosmic distances, silently orchestrates the movements of planets, stars, and galaxies. Though imperceptible in a cup of tea, it is gravity that binds the cosmos, guiding the motion of planets in their elliptical paths, pulling gas and dust together to birth stars, and maintaining the delicate balance of galaxies. Then there is the electromagnetic force, the architect of chemistry. Unlike gravity, it dominates the atomic realm, governing how electrons move around nuclei, how atoms bond to form molecules, and how light interacts with matter. Electrons are held by protons in the nucleus by this force, and it is this same invisible interaction that allows magnets to cling to refrigerators, that enables the transmission of electricity powering our cities, and that makes light itself possible. Without the electromagnetic force, atoms would not form, molecules would not exist, and life would be impossible. Next, the strong nuclear force, a titan confined to the tiny heart of atoms. Protons, each carrying a positive charge and naturally repelling each other, are held together by this force in a fierce, invisible grip. It is unimaginably powerful, capable of binding the nuclei of atoms against forces that could tear them apart. Every gram of matter owes its stability to this silent, relentless force, and it is this same force that releases the titanic energy of stars, from the gentle warmth of our sun to the cataclysmic explosion of supernovae. Finally, the weak nuclear force, subtle yet essential, governs the processes of decay, the transformations of particles, and the alchemy of elements in stars. Through it, one type of particle can morph into another, releasing energy in ways that sustain stars and create the elements that will one day form planets, oceans, and life itself. It is the quiet sculptor of change at the subatomic scale, invisible to our eyes, yet critical for the universe's evolution. Now, let us descend from these abstract forces to the tangible consequences they produce: chemical reactions. Every reaction is a story of energy, a negotiation of electrons, a transformation of matter from one state to another. Consider the lightning storm, a brilliant arc of electricity tearing across the sky. Within this flash, nitrogen and oxygen molecules collide with immense energy, forming compounds that fertilize the earth. Each spark is a microcosm of the energetic ballet that underlies the chemistry of life. In the oceans, molecules interact in a complex web, forming clusters and networks that scientists are only beginning to understand. Water, seemingly simple, is a miracle of hydrogen bonding, capable of dissolving more substances than any other liquid, supporting oceans, lakes, and rivers, and regulating the climate of entire planets. Within each drop, countless interactions unfold every nanosecond, invisible yet essential, dictating how nutrients flow, how life thrives, and how ecosystems endure. Consider life itself, the machinery of cells, the complex networks of proteins, nucleic acids, and lipids. Inside each cell, molecules move with precision, guided by forces that are imperceptible yet unerring. Proteins fold into intricate shapes, each determined by the tug-of-war of atomic forces, creating enzymes that catalyze reactions millions of times faster than they would occur naturally. DNA coils and uncoils, reading and copying information, a dynamic script written in the language of chemistry. And every heartbeat, every thought, every movement arises from this invisible choreography. But the story does not stop at biology. Forces at the atomic level echo across the universe. The same electromagnetic interactions that allow electrons to bind to nuclei in your body govern the formation of stars and galaxies. The strong nuclear force fuels stellar cores, creating elements that will one day form planets. The weak force drives the decay of particles, a cosmic clock that orchestrates the timing of events across billions of years. Even our human technologies are echoes of these fundamental forces. Every microchip, every laser, every electric motor is a testament to our ability to harness the forces that nature has perfected over eons. By understanding atoms, electrons, and the subtle forces that govern their behavior, we have transformed the world, creating civilizations, communications, and machines once unimaginable. As we explore these forces, as our journey continues, we cross a threshold where the familiar laws of the world begin to blur and dissolve. Here, in the heart of the quantum domain, the rules of reality shift. Certainty becomes possibility. Objects become waves, and the universe reveals that beneath its surface lies a logic stranger and more elegant than anything we encounter in daily life. To understand chemistry at its deepest level, we must walk carefully into this landscape of quantum mechanics, a realm where intuition falters and only curiosity can guide us. Imagine a world where objects have no single position, where motion happens in discrete jumps, and where the very act of observing changes what is observed. This is the quantum world, delicate yet powerful, invisible yet foundational. Let us begin with the wave-particle duality, the first crack in the classical view of nature. For centuries, light was thought to be a wave. Then, particles of light, photons, entered the story, revealing that even something as steady as illumination can behave like tiny packets of energy. But the revelation didn't stop there. Electrons, once imagined as solid particles orbiting nuclei, also revealed a dual identity, sometimes particle, sometimes wave. This duality is not a trick or an illusion. It is the fundamental truth of the microscopic world. Picture an electron not as a bead of matter, but as a spread-out cloud of probability, a shimmering field of possibilities. Until measured, it does not occupy a single point. It exists in many potential states at once, and when it interacts with other electrons, the waves of probability interfere, merge, and separate, giving rise to the shapes of orbitals that dictate chemical bonds. The geometry of matter emerges from the mathematics of waves. Now consider quantization, the rule that energy comes in discrete levels rather than continuous values. In the macroscopic world, a car can accelerate smoothly, a dimmer can brighten a room gradually. But in the atomic world, electrons cannot choose arbitrary energies. They can only occupy specific quantized levels. This is why atoms emit light in precise colors when energized. The electron jumps from one level to another, releasing a photon whose energy corresponds exactly to the difference. This rule, so tiny and subtle, shapes the beauty of neon signs, the glow of stars, the photosynthesis in plants, and even the color of your eyes. Let us descend deeper, beneath the quantized levels, to the Pauli exclusion principle, a rule that forbids electrons from occupying the same quantum state. This single principle explains the structure of the periodic table, the diversity of elements, and the stability of matter. Without it, atoms would collapse into each other. There would be no chemistry, no molecules, no life. The universe as we know it would be crushed into a dense chaos of identical particles. Instead, variety emerges. Carbon becomes carbon, oxygen becomes oxygen, and the universe gains the richness required for stars, oceans, and living beings. But the quantum world is not only governed by exclusion, it is also shaped by uncertainty, the idea that we cannot know both the position and momentum of a particle precisely at the same time. This is not a limitation of technology. It is a fundamental property of nature. The more accurately we know where an electron is, the less we know about how it moves. This uncertainty gives rise to zero-point energy, the restless motion that prevents atoms from ever being fully still, even at absolute zero. In this uncertainty lies the secret of chemical reactivity. Electrons can tunnel through barriers they should not be able to cross, enabling reactions that would be impossible in a purely classical world. In stars, quantum tunneling allows hydrogen nuclei to fuse into helium, releasing the energy that warms planets and lights galaxies. On Earth, tunneling allows enzymes to accelerate reactions billions of times faster than they would occur otherwise, enabling the very processes that sustain life. Now, let us explore entanglement, perhaps the most mysterious quantum phenomenon of all. When two particles interact, their states become linked in a way that transcends space itself. Change the state of one, and the other responds instantly, even if separated by light years. This connection does not allow communication faster than light, but it reveals a hidden unity in the fabric of reality. Chemistry, too, relies on this phenomenon. Electrons in chemical bonds become entangled, sharing properties across space in ways that stabilize molecules and shape their reactions. Quantum rules also govern the motion of electrons in solids. In metals, electrons form a sea, able to flow freely and conduct electricity. In insulators, the electrons are locked in place, unable to move. In semiconductors, the heart of modern technology, electrons occupy a delicate balance, jumping from one band to another under the influence of charge, light, and temperature. This quantum balance makes computers possible, phones intelligent, and satellites functional. The universe does not build its masterpieces with randomness. Every molecule that exists, from the fragrance of a rose to the venom of a cobra, from the glucose fueling your neurons to the ozone shielding your planet, is the result of geometry sculpted at the quantum scale. In this chapter, we step into this hidden architecture, a blueprint written without ink, drawn without edges, and yet shaping everything you see, breathe, taste, and become. At the beginning of molecular geometry lies a simple truth. Electrons hate being too close to each other. Their mutual repulsion, subtle as a whisper and yet powerful as a cosmic law, forces them into arrangements that minimize conflict. Valence shell electron pair repulsion, or VSEPR, is our entry point into this quantum ballet. Imagine a council of electron clouds negotiating space, each claiming territory around the nucleus, spreading themselves as far apart as possible. The shape that emerges is not arbitrary. It is the most peaceful configuration nature permits. A methane molecule adopts its tetrahedral design not because carbon prefers elegance, but because 4 electron domains push away from one another until they stand at perfect corners of an invisible triangular pyramid. This is geometry born from tension, harmony rising from repulsion. That geometry decides everything: reactivity, polarity, states of matter, solubility, stability. A few angstroms in angle can determine whether a molecule becomes a nutrient or a neurotoxin. As molecules grow more complex, the plot thickens. Electron domains are no longer simple dots or lines. They morph into hybrid orbitals. The carbon in ethylene blends its atomic orbitals into sp2 hybrids, flattening itself into a planar arrangement, while benzene pushes geometry further into a cyclic resonant stable symphony. Hybridization is not a trick of convenience. It is a structural negotiation between energy, shape, and bonding efficiency. Orbitals stretch, shrink, blend, and overlap to craft molecular architectures with precision more delicate than any human hand could ever replicate. Beyond single atoms and small molecules lies a kingdom of complexity: macromolecules, polymers, biomolecular frameworks, and crystalline lattices. Each follows geometric laws carved by the quantum world. The double helix of DNA does not twist by accident. Hydrogen bonds, base stacking, and steric interactions gently torque the molecule into its famous spiral staircase. Proteins, too, fold into astonishing shapes determined by dihedral angles and intermolecular forces, from alpha helices coiled like nanosprings to beta sheets stretched like molecular tapestries. The geometry is not merely structural, it is functional. Fold something incorrectly, and a protein becomes useless or even deadly. Even the materials that shape our cities owe their strength to atomic geometry. Diamond's unmatched hardness emerges from its three-dimensional tetrahedral carbon network, while graphite's soft, layered structure arises from two-dimensional sheets of hexagonal carbon lattices gently held together by van der Waals forces. The same element, carbon, expresses two radically different personalities simply because its atoms adopt different geometries. Zoom in further, and geometry becomes even stranger. Water, the most familiar molecule on Earth, hides its quirks behind bent geometry and hydrogen bonding. The slight angle between its hydrogen atoms creates polarity, which in turn produces everything from surface tension to ice's unique expansion upon freezing. This small geometric asymmetry is the reason lakes don't freeze from bottom to top, protecting aquatic life through the winter. Geometry becomes survival. In the inorganic world, geometry commands color. Transition metal complexes absorb specific wavelengths of light because their d orbitals split into geometrically determined energy levels. Change the ligands or distort the geometry, and the colors shift like moods in a chameleon. Crystals grow in intricate patterns because ions organize themselves into repeating geometric motifs dictated by charge. Balance and spatial symmetry. Symmetry itself is a silent architect woven into the heart of chemistry. A molecule with perfect symmetry is often unreactive, stable, and energetically content. Break that symmetry, twist a bond, distort an angle, introduce an asymmetric center, and new possibilities awaken. Chirality appears where molecules become left-handed or right-handed versions of themselves, identical in composition yet profoundly different in behavior. One can heal, the other can harm. Geometry decides. On cosmic scales, the same principles echo. Interstellar molecules drifting between stars adopt geometries that affect how they emit or absorb radiation. Astronomers decode these signatures to detect molecules from worlds away. Geometry becomes a message written across the sky. As we travel deeper into this molecular architecture, we realize that chemistry is not merely the study of substances. It is the study of shapes, of spatial negotiations, of quantum cartography, etched into matter itself. Geometry is the language atoms think in, the grammar they follow, the blueprint they construct. And as you peer into this invisible design, the universe begins to look less like chaos and more like a grand cathedral built from particles, angles, and forces. To understand chemistry is to understand the silent forces that bind the universe together. They do not roar like storms or blaze like stars. They operate quietly, threading atoms into molecules, molecules into materials, and materials into the fabric of everyday life. These forces are subtle, often invisible, and yet they rival gravity in their power to sculpt reality. In this chapter, we explore them not as equations, but as living dynamics that guide matter's every motion. At the foundation lies the simple question, why do atoms bond at all? An isolated atom drifts with a restless energy, incomplete, unsatisfied, like a single note longing for harmony. When atoms approach one another, their electrons interact, orbitals overlap, and a negotiation begins. If the union lowers the total energy, a bond forms. If it raises the energy, the atoms recoil. Chemistry is born from this negotiation between attraction and repulsion, a delicate ledger of stability managed by quantum bookkeeping. Covalent bonding emerges from shared electron clouds. Here, two nuclei pull on the same electron pair, balancing their attractions like two hands holding a rope from opposite ends. The rope does not belong to either hand. It exists between them. This shared existence gives the molecule identity. Some covalent bonds are as gentle as a whisper, easily broken. Others, like in diamond, are fierce and unyielding, forging networks harder than any metal forged by human ambition. Ionic bonding transforms the landscape further. When one atom relinquishes an electron to another, their identities shift permanently. A metal becomes positively charged, a nonmetal negatively charged, and the electrostatic pull between these opposites creates a crystalline fortress. Sodium chloride, a grain of salt resting on your tongue, is built from billions of these alternating ions locked into an ordered lattice that shatters under pressure, yet dissolves instantly in water's polar embrace, metallic. Bonding spreads electrons like a shimmering ocean. Each atom contributes its outer electrons to a communal sea, creating conductivity, malleability, and a luster that has fascinated humanity since the first sunrise reflected on a copper blade. This electron sea flows freely, enabling electricity to pass through metals with the elegance of a silent current. But chemistry doesn't end at bonds. It thrives in the spaces between them, in weaker interactions that may go unnoticed, yet hold massive influence. Hydrogen bonding, van der Waals attractions, bistecking, dipole interactions. These forces orchestrate the folding of proteins, the structure of DNA, the properties of liquids, the patterns of crystals, the behavior of gases. They are the subtle hands that guide matter's choreography. Consider hydrogen bonding, the quiet architect of water's extraordinary personality. These bonds are fleeting and delicate, yet strong enough in numbers to make water expand when frozen, absorb heat without boiling instantly, and dissolve more compounds than nearly any liquid in existence. Life depends not on water's solidity or fluidity alone, but on the constantly shifting hydrogen bonding network that gives it flexibility and resilience. Beyond the forces that bind molecules lie the energies that drive reactions. Every bond carries a certain energy, and breaking or forming bonds requires the universe to pay or receive energy like currency. Activation energy stands as a gatekeeper, demanding payment before a reaction proceeds. This gate is not merely a hurdle, it is a guardian of stability. Without activation energy, substances around you would react spontaneously and chaotically. Wood might ignite by touch, metal might rust instantly, oxygen might combine uncontrollably. Activation energy maintains order. Energy does not vanish or appear from nowhere. It is transformed. A reaction releases energy when the bonds formed are stronger than the bonds broken. Combustion, metabolism, and polymerization all release energy that fuels life, engines, and industry. Endothermic processes absorb energy, storing it like seeds storing sunlight, waiting for the right moment to release it again. Catalysts enter this story as the silent negotiators. They do not take part in the reaction's beginning or end, yet they reshape the path, lowering the activation energy, smoothing the journey, and guiding reactants to products with efficiency nature alone once commanded. Enzymes, the biological catalysts, are masterpieces of evolutionary engineering. They can speed up reactions millions of times, operating with a precision that makes human chemistry look crude by comparison. In industrial settings, catalysts shape everything from fertilizers to plastics, medicines to fuels. They accelerate progress, reduce waste, and direct molecules like conductors guiding a symphony. Without them, modern life would slow to a crawl. Caught in the inefficiency of unguided reactions, deep within this interplay of forces, we encounter potential energy surfaces, vast landscapes where valleys represent stable molecules and peaks represent high-energy states. Every chemical reaction is a journey across this terrain. Molecules climb hills, tumble into valleys, transition through passes, and settle into configurations determined by quantum mathematics. Chemists map these landscapes not with compasses, but with computation, spectroscopy, and intuition honed by centuries of observation. This exploration reveals a profound truth. Chemistry is not chaos. It is structure informed by force, stability defined by energy, transformation guided by probability. Every bond, every molecule, every crystal, every reaction is part of a grand system where energy and structure converse to craft the physical world. As we reach the end of this chapter, the picture grows clearer. The forces that hold matter together are not merely interactions. They are the universe's stitching. They tie particles into purpose, shape substances into function, transform raw matter into life, light, movement, and meaning. Without them, the universe would be a silent fog of atomic loneliness. With them, reality becomes architecture, and still, deeper forces remain to be explored. Step beneath the surface of matter, and the world dissolves into something stranger than imagination. At this scale, logic bends, certainty fades, and the universe is stitched not with lines, but with probabilities. In this chapter, we enter the quantum landscape, the invisible architecture that defines how electrons occupy space, whispering instructions to atoms, molecules, and materials across the cosmos. An electron does not behave like a planet, nor does it orbit the nucleus in tidy circles. Instead, it exists as a cloud of possibility, spreading through space in a wave of presence and potential. The Schrödinger equation, the quiet mathematical heart of quantum mechanics, does not tell us where the electron is, but where it could be. Each solution to this equation becomes an orbital, a region where the electron's existence is statistically favored. These orbitals are not drawings. They are three-dimensional probability fields woven from wave functions shaped by energy, symmetry, and quantum rules older than stars. The simplest of these shapes is the one's orbital, a spherical cloud hugging the nucleus like a soft halo of likelihood. As energy levels rise, orbitals unfold into more elaborate geometries, dumbbells stretching across space, clover shapes twisting into angles, and even delicate hybrid forms blending into one another. These designs are the fingerprints of the quantum world, and they dictate how atoms bond, react, vibrate, and assemble. Within each orbital lies a set of quantum numbers, the coordinates of the electron's identity. The principal quantum number defines its energy. The angular momentum number dictates its shape. The magnetic number determines its orientation, and the spin number assigns its intrinsic rotation. These four values act as the electron's passport, distinguishing it from every other electron in the universe. And then comes Pauli with his exclusion principle, a quiet rule that changes everything. No two electrons can share the same set of quantum numbers. This single restriction, subtle yet absolute, generates the periodic table structure, atomic behavior, and the diversity of chemistry itself. It forces electrons into distinct orbitals, stacking them layer by layer, shaping the very identity of elements. Hydrogen remains simple with one electron. Carbon grows creative with 6. Iron becomes magnetic with unpaired d electrons. Xenon becomes noble with its filled shells. Life, color, magnetism, conductivity all emerge from this elegant rule. Electrons do not merely occupy orbitals. They resonate, shift, hybridize, and reorganize in response to energy, light, and interactions. When atoms approach, their orbitals blend into molecular orbitals, new regions where electrons belong to neither atom alone, but to the bond between them. These orbitals govern stability. Bonding orbitals pull nuclei together, antibonding orbitals push them apart, and non-bonding orbitals hover like quiet spectators. In conjugated systems, electrons spread even further, delocalizing across multiple atoms in shimmering patterns of resonance. Benzene, with its extraordinary stability, exists not as 6 alternating bonds, but as a continuous cloud of electron density circulating around the ring. This delocalization shapes everything from pigments to pharmaceuticals, conductivity to aromaticity. Electrons, once thought of as point particles, become the authors of intricate molecular symphonies. The quantum landscape extends into excited states. When light strikes a molecule, an electron may absorb its energy and leap into a higher orbital. This jump is fleeting, yet it triggers processes that power photosynthesis, drive vision, create fluorescence, and enable solar cells. Excited states rewrite electron distributions, alter bond strengths, and momentarily reshape molecular geometry. The return to the ground state often releases energy as heat or light, crafting the glow of bioluminescent organisms and the shimmer of neon signs. Below this energetic choreography lies another truth: uncertainty. Heisenberg's principle whispers that no electron can reveal its exact position and momentum simultaneously. This uncertainty is not a limitation of tools. It is a law of nature. Electrons inhabit a reality where precision dissolves into probability, where existence is smeared across space like ink melting into water. This uncertainty gives rise to tunneling, a phenomenon both subtle and miraculous. Electrons can slip through energy barriers without the energy to climb over them. They tunnel through walls of possibility, enabling reactions that classical physics forbids, powering processes like enzyme catalysis, nuclear fusion in stars, and even the working of scanning tunneling microscopes that map surfaces atom by atom. In the quantum landscape, electrons influence each other even across distance. Exchange interactions, spin pairing, and electron correlation shape magnetism, superconductivity, and chemical reactivity. The dance is not random. It is choreographed by mathematics, symmetry, and the delicate balance of energy. As we explore these quantum structures, the world above begins to look different. Copper conducts electricity because its electrons roam freely through metallic orbitals. Chlorophyll captures sunlight by shuttling electrons between states. Silicon becomes the backbone of computers through controlled electron movement in semiconductors. Diamonds sparkle because their electrons create a wide band gap, absorbing only deep ultraviolet light. Quantum behavior is not a curiosity at the fringes of physics. It is the engine of nearly everything modern, ancient, natural, and technological. The quantum landscape is a paradoxical realm. It is structured yet uncertain, ordered yet fluid, invisible yet omnipresent. To understand it is to see the hidden architecture beneath reality's surface, a lattice of probabilities sculpted into form by mathematics and energy. Matter does not simply exist. It unfolds, vibrates, resonates, and reorganizes through the rules of this landscape, following principles that defy common sense yet define existence. And as our journey continues, the deeper layers of this architecture begin to reveal themselves. Every transformation in the universe, from the rusting of iron to the metabolism of a single sugar molecule inside a living cell, follows a quiet script. Reactions are not chaotic collisions. They are orchestrated journeys through invisible pathways, guided by energy landscapes, intermediates, and fleeting states that exist for less than the blink of a photon. In this chapter, we travel into these pathways, not as observers but as explorers, decoding the secret logic of chemical change. At the heart of every reaction lies a potential energy surface, a rolling terrain where molecules climb slopes, fall into valleys, and pass through high-energy gateways known as transition states. The reactants do not instantly become products. They must navigate this landscape with precise motions, bending bonds, shifting electron density, twisting into shapes that last only an instant. These shapes cannot be seen directly, but their fingerprints appear in energy diagrams, spectroscopic signatures, and computational models. They are the whispers of structure in moments too brief for normal existence. As reactants approach one another, their electron clouds stretch, polarize, and distort. They respond like dancers adjusting to each other's movement, testing compatibility before committing to transformation. If the path demands too much energy, the reaction hesitates, waiting for thermal fluctuations or light, or a catalyst to push it forward. If the path is gentle, the reaction proceeds spontaneously, flowing downhill like water, finding its way through stone. Mechanisms bring order to this invisible movement. They reveal that reactions often unfold in a series of steps, each with its own barriers, intermediates, and micro-decisions. Even a simple substitution in organic chemistry can follow different routes depending on environment. In one pathway, the attacking group strikes while the leaving group simultaneously departs, creating a concerted motion where bonds break and form in the same heartbeat. In another, the molecule first loses a group, forming a charged intermediate that briefly stands alone, exposed to the world, waiting for the next participant to arrive. These differences define rates, products, selectivity, and behavior. In elimination reactions, molecules shed atoms like travelers, discarding unnecessary belongings. Bonds rotate, protons shift, and electrons reorganize to craft double bonds, transforming saturated frameworks into leaner, more reactive structures. Even here, mechanisms shape destiny. A base pulling a proton can cause one outcome. A charged intermediate rearranging itself can create another. Chemistry's rules are firm, yet possibilities remain abundant. But reactions are not limited to small molecules. Chain reactions can unlock cascades where one event births another and another and another, multiplying energy and momentum across a system. From radical polymerizations to atmospheric ozone cycling, these cascades can build materials or devastate ecosystems. A single radical drifting through the air can set off a chain that reshapes entire atmospheric layers, influencing climate, radiation, and life itself. In biochemistry, the mechanisms grow more intricate. Enzymes carve pathways with astonishing precision, guiding substrates into active sites crafted with the delicacy of molecular architecture. They hold molecules in exact orientations, applying pressure, twisting angles, stabilizing transition states, and lowering energy barriers with efficiency unmatched in the industrial world. A reaction that might take centuries in a test tube completes within milliseconds inside a cell, powered not by brute force, but by elegance of design. Inside these enzymatic pockets, mechanisms unfold like grand stories. Proton shuttles transfer charges across networks. Cofactors act as small chemical assistants. Metal ions bend electron density, activating bonds for the next step. Substrates undergo transformations so specific that even a mirror image molecule would be rejected. Life depends on such precision. One incorrect mechanism could collapse an entire biological process. Beyond living systems, inorganic reactions shape geology, atmosphere, and technology. Redox processes move electrons between species, powering batteries, corrosion, and metabolism. Photochemical reactions harvest sunlight, promoting electrons into excited states and triggering radical cascades that craft everything from vitamin D in your skin to ozone in the stratosphere. Coordination complexes shift ligands through reorganizations as graceful as chess strategies, producing catalysts that guide industries and medicines that target specific biological pathways. Every reaction carries a motive force. Thermodynamic favorability determines where the system wants to go. Kinetics determines how quickly it gets there. A reaction may be energetically favorable, yet impossibly slow without assistance. Another may be rapid, yet lead to less stable products, depending on its pathway. Chemistry becomes a balance between desire and opportunity, between stability and accessibility. Within these pathways lie strange events that defy intuition. Carbenes appear like ghosts, reactive, fleeting, reshaping molecules with selective violence. Sigmatropic rearrangements move atoms across frameworks without ever breaking the overall skeleton. Pericyclic reactions unfold through concerted electron shift, guided by symmetry rules that seem mystical, yet arise from pure quantum logic. Molecules sense these rules without consciousness, following them with unwavering obedience. Then come the rearrangements, molecular migrations, where atoms relocate to more stable positions, sometimes flipping entire structures inside out. A hydride can move across a carbon network like a traveler finding better lodging. A methyl group can migrate, forming new bonds with the inevitability of gravity. These rearrangements, unpredictable to beginners, become predictable to those who understand the underlying geometry of transition states. Reactions are not merely transformations. They are negotiations between energy and structure, shaped by mechanisms that decide who moves first, who waits, who leaves, and who remains. Each mechanism is a story, each step a scene, each intermediate a character existing between two states of reality, and as we explore these pathways, the invisible world becomes clearer. Chemistry is not a blur of collisions. It is choreography, a sequence of moves dictated by forces, geometry, and energy. It is the logic behind all transformation, from the flicker of a flame to the replication of DNA. The journey through these mechanisms reveals a truth as profound as it is subtle. Nothing changes without reason, and every reaction carries the memory of its path. Our exploration continues deeper still. Reactions do not happen in isolation. They unfold within a medium, a silent environment that cushions molecules, guides them, speeds them, slows them, dissolves them, or locks them into place. This environment is the solvent, an unseen stage upon which all molecular drama performs. Though often overlooked, solvents dictate the pace and direction of chemistry with an influence so strong it borders on invisible governance. In this chapter, we enter the realm of solvents, where the medium becomes as important as the message. A solvent is more than a liquid. It is a network of interactions, a dynamic landscape where molecules drift, rotate, collide, and evolve. Each solvent possesses a personality shaped by polarity, hydrogen bonding capacity, dipole strength, viscosity, and dielectric constant. These attributes create microenvironments that alter reaction rates, stabilize intermediates, and select pathways. Change the solvent, and you often change the entire destiny of a reaction. Consider water, the universal solvent, not because it dissolves everything, but because it interacts with everything. Its polarity pulls apart ionic crystals. Its hydrogen bonds stabilize charged intermediates. Its structure forms dynamic clusters, constantly forming and breaking, surrounding solutes with hydration shells that insulate, protect, and sometimes hinder. In aqueous media, acids and bases behave differently. Protons glide across hydrogen bond networks like lightning, zipping through a storm cloud. Water is never passive. It participates, influences, guides. Move to polariprotic solvents, and the story shifts dramatically. Acetonitrile, dimethyl sulfoxide, acetone. These liquids do not donate hydrogen bonds, but their strong dipoles stabilize cations with remarkable efficiency. Anions, however, remain relatively free, unshielded by solvent cages. This freedom accelerates nucleophilic reactions that would otherwise drag their feet in water. A reaction that creeps slowly in a protic solvent can sprint when placed in a polar aprotic medium. Mechanistic preferences flip, pathways reorganize, selectivity changes. Solvents act like invisible hands rearranging molecular choreography. Nonpolar solvents, in contrast, create environments of gentle indifference. Hexane, toluene, cyclohexone, these liquids provide little stabilization to ions, but they nurture subtle interactions like van der Waals forces and pi stacking. In such media, ionic mechanisms falter, but radical pathways awaken. Molecules move with minimal friction, and reactions driven by light or heat find clarity. Aromatics dissolve in aromatics, alkanes dissolve in alkanes, and delicate equilibria emerge that would collapse instantly in water. The absence of strong interactions becomes a feature, not a flaw. Beyond simple polarity, solvent dynamics influence the microarchitecture of reactions. Viscosity alters how rapidly molecules encounter one another. In thick solvents, diffusion slows, giving long-lived intermediates more room to breathe. Fast reactions may stall, while slow equilibria become dominant. Temperature shifts amplify these effects, turning solvents into thermal regulators that can freeze reactions or accelerate them into explosive cascades. Solvation, the process by which solvent molecules surround solids, is an entire universe of its own. For ionic species, solvation determines stability. For neutral molecules, solvation influences orientation, shape, and reactivity. Solvent cages can trap reactive intermediates, protecting them from premature destruction. At other times, these cages break open, allowing pathways that would otherwise remain impossible. Even the geometry of solvation affects outcomes. Tightly bound solvation shells favor one reaction path. Loosely bound shells favor another. In biological systems, the role of solvent becomes even more astonishing. Water inside cells is structured, layered, and subtly constrained by proteins, membranes, and ions. This water does not behave like bulk water. It forms hydration layers, supports proton transfer, molds enzyme active sites, and directs folding pathways. Inside these microscopic environments, reactions unfold with precision that industrial chemistry can only dream of. Life itself is a solvent-mediated miracle. Supercritical fluids push the idea further, existing in a state where liquid and gas blur into one. Supercritical carbon dioxide, with its tunable density and exceptional diffusivity, dissolves materials unpredictably yet operates cleanly. It extracts flavors, cleans surfaces, polymerizes materials, and supports reactions with environmental gentleness. It is a solvent that challenges the boundaries of matter itself. Ionic liquids, molten salts at room temperature, introduce another frontier. Their charged components create strong solvent fields that stabilize unusual species, promote green chemistry, and dissolve compounds once thought insoluble. Their lack of vapor pressure makes them environmentally friendly, while their tunable structures open nearly infinite chemical possibilities. In their strange embrace, catalysts behave differently, polymers form uniquely, and reaction mechanisms reveal alternative pathways. Deep eutectic solvents continue this revolution. Formed by mixing two solids that melt into a liquid, they offer properties beyond conventional solvents: biocompatibility, tunability, and the ability to dissolve both organic and inorganic species simultaneously. They democratize reactions, making previously complex transformations accessible with simplicity. In industrial chemistry, solvents determine scalability, cost, safety, and environmental impact. A reaction may be efficient in theory, but if the solvent is toxic, volatile, expensive, or environmentally damaging, the process becomes unsustainable. Green chemistry initiatives push for safer, cleaner solvents embracing water, supercritical CO2, and bio-derived liquids that reduce waste and protect ecosystems. Inside living organisms, solvent orchestration becomes rhythmic. Cytoplasm behaves like a structured. In this chapter, the story of chemistry enters its strangest corridor, where every rule you thought was permanent begins to wobble like a reflection on rippling water. This is the territory where molecules behave like riddles, where matter stalls between identities, and where reactions evolve a second personality. The quantum edge is not a place. It's a behavior, a mood of nature that appears when conditions become extreme, or when molecules are pushed into extraordinary situations. Inside this realm, electrons forget their favorite orbitals and begin borrowing ones they shouldn't have access to. Bonds loosen without breaking, stretch without snapping, and sometimes reconstruct themselves into shapes that would leave classical chemists blinking in disbelief. Reactions no longer move on straight highways. They meander through twisting, probabilistic tunnels where transition states aren't just peaks on an energy landscape, but entire neighborhoods of possibilities. Here, familiar concepts like acidity, polarity, oxidation state start behaving like shadows under an eclipse. They're still real, but distorted by quantum influences that pull molecules into unexpected geometries. The line between reactant and product becomes a smear of possibility, a region where molecules flicker in transitional forms so brief they exist only as mathematical probabilities. This is also the zone where catalysts reveal their true depth. Rather than acting like simple choreographers that guide reactions, catalysts become shapeshifters. They temporarily rewrite the landscape of molecular interactions, bending energy profiles, twisting orbital alignments, and giving new shortcuts to transformations that would be otherwise impossible. Under extreme pressures or ultra-low temperatures, catalysts gain startling abilities. Their interactions start behaving like synchronized wavefronts, guiding electrons through resonance patterns rather than pushing them mechanically. Inside biological systems, quantum edges appear everywhere. Inside enzyme pockets where reactions occur at speeds that defy classical rates. Inside DNA, where electrons hop across bases with eerie precision. And inside the human brain where certain molecular effects whisper with quantum undertones. The living world at its deepest level negotiates with probability rather than certainty. Venture further into the quantum frontier and you meet tunneling, a phenomenon so bizarre it feels fictional. Particles slip through barriers they have no energy to climb over, like ghosts drifting through a wall. In chemistry, tunneling allows hydrogen atoms to influence reactions on timelines that would be impossible otherwise. At ultra-cold temperatures, tunneling doesn't just contribute, it dominates, steering reactions toward pathways that traditional thermodynamics wouldn't predict even in its wildest dreams. Chemical systems near absolute zero unveil yet another layer. Molecules lose their individuality and behave like coordinated patterns, as if the universe presses a mute button on thermal chaos. Superfluids glide with impossible smoothness. Magnetic behaviors crystallize into quantum lattices, and atoms form collective waveforms that move with eerie cooperation. Chemistry shifts from being a battlefield of collisions into a ballet of coherent waves. By the edge of this domain, you begin to see chemistry merging with physics, computation, and philosophy. Wave functions aren't just equations. They become living stories of what matter can become. Probability isn't uncertainty, it's potential. Molecules stop being objects and start becoming processes. Events, tendencies, and through all of this, one truth keeps echoing. The deeper one travels into the quantum edge, the more one realizes that chemistry is not built from particles, it is sculpted from possibilities. In this final chapter, we step into a landscape that doesn't fully exist yet. A space shaped by theory, imagination, and the quiet hum of experiments still running in dark laboratories around the world. Here, chemistry becomes a prediction engine for realities not yet born. Quantum rules are no longer just explanations of how atoms behave. They become the drafting tools for the next century of human innovation. The story begins with a simple idea. If you can understand the wave function of a system, you can predict its future. But predicting that wave function for anything more complex than a hydrogen atom becomes a labyrinth of equations so dense they resemble cosmic poetry. That's where quantum computing enters the narrative like a new protagonist. Unlike classical computers that chop information into bits, quantum machines operate as superpositions of states, weaving entire branches of possibility in parallel. For chemistry, this is nothing short of a revolution waiting in the wings. The molecules that took decades to model could be simulated in moments. Reaction networks that seem random could be forecast with clarity. Material discovery, drug design, atmospheric chemistry, renewable fuels, each could be accelerated in ways that reshape civilization. Meanwhile, experimental chemistry is quietly converging with this revolution. Lasers now act like surgical instruments for electrons, slicing through orbital structures, rearranging bonds, freezing reactions mid-motion to photograph their quantum skeletons. Ultrafast spectroscopy captures transitions so brief they occur within femtoseconds. With these tools, chemists aren't observing reality anymore. They're stepping into it, guiding transformations as they unfold. As pressure increases or temperature collapses toward absolute zero, the periodic table behaves like an expanding universe of alternate personalities. Elements that seem mundane at room conditions become exotic under extreme regimes. Carbon forms quantum cages, hydrogen turns metallic and superconductive, and xenon, long considered inert, begins forging unexpected compounds. These discoveries hint that the world we know is only a mild version of what matter can become. At the same time, the borders between chemistry and biology blur even further. Quantum effects, once considered too fragile for life, turn out to be deeply embedded in photosynthesis, enzyme efficiency, and even sensory perception. Nature, it seems, has been running quantum algorithms for millions of years. Human science is merely catching. As our journey reaches its quiet horizon, we step out of equations, beyond orbitals, past the vibrating lattice of atoms, and into a broader reflection. After exploring the territories where particles blur, bonds breathe, and matter negotiates with probability, we find ourselves meeting a truth both humbling and grand. The universe is an unfolding conversation, carried by the language of chemistry and whispered through quantum rhythms. Across every chapter in this exploration, a pattern kept emerging like a signature woven across space. Atoms rearranged not because they wanted to, but because the universe presented paths of possibility. Electrons shifted their clouds to accommodate new patterns. Molecules formed, broke, rebuilt, and transformed, all driven by tendencies, not commands. The quantum world doesn't operate through rigid scripts. It improvises, shifting from moment to moment like a cosmic musician adjusting the melody to match the room. In this epilogue, the story becomes personal. Consider your breath. Within it, trillions of molecules negotiate quantum probabilities, forming fleeting interactions before they drift away again. Every inhale is a chemical remix. Every heartbeat is powered by quantum-scale electron transfers. The fact that life persists at all is evidence that the universe prefers structure even while bathing in uncertainty. From this vantage point, one realizes that mystery isn't a problem to be solved. It's a space to stand inside. A region where curiosity becomes a tool not just for science, but for being human. Quantum chemistry teaches us that the most important transformations are small, invisible, improbable, and yet they shape everything. As laboratories around the world continue their quiet work, new discoveries echo through disciplines, quantum-controlled photochemical reactions, catalysts tailored so precisely they behave like molecular personalities, exotic materials that bend the rules of conductivity and magnetism, biological motors driven by tunneling. Each finding is not an ending, but the opening line of a new chapter. We step away with an understanding that the universe is more flexible than we thought, more poetic, more willing to bend. And in that bending lies possibility. This is not a farewell to quantum chemistry. It is an invitation to keep exploring the invisible, because the invisible is where the future is born. From the smallest particles to the edge of the imaginable, we journeyed through a universe built from probabilities, shaped by waves and illuminated by curiosity. The story of quantum chemistry is not just the story of atoms. It is the story of every transformation taking place around you, within you, and far beyond the horizon of human vision. As you leave this episode, remember that the world you interact with isn't solid in the way it appears. It's a lattice of fleeting certainties, stabilized only long enough for you to experience meaning. Every material object, every chemical scent, every glimmer of color, every charge that flows through a circuit, each one is sculpted by quantum rules acting in silence. The questions we ask today are not finished. They will continue unfolding inside labs, telescopes, equations, and imaginations across the world. Because the search for understanding is not a straight path, it is a fractal, branching into new directions with every answer we uncover. This is the essence of science, a horizon that moves as fast as you approach it. This was the Wonder Lab. Until next time, keep questioning the familiar, keep exploring the unseen, and keep stepping into the world with the curiosity that shapes discoveries. The universe is not waiting to be understood. It is waiting to be explored.